Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1910. The intellectual landscape of mathematics was undergoing a profound transformation, a shift away from the concrete and towards the abstract. Ernst Steinitz, a name that would become synonymous with the very foundations of modern algebra, published a paper that would forever alter the course of field theory, titled Algebraic Theory der Körper, or Algebraic Theory of Fields. This work was a landmark achievement, a cornerstone upon which much of subsequent algebraic development would be built. It presented a unified, axiomatic approach to the study of fields, providing a framework for understanding their structure, their extensions, and their fundamental properties. This paper was a combination of existing ideas, a synthesis of earlier work, and a bold leap forward, solidifying Steinitz's place among the mathematical giants of his era. Before Steinitz, the study of fields, while present, lacked the cohesive, axiomatic structure that would become its hallmark. Mathematicians grappled with fields primarily through the lens of specific examples, such as the rational numbers, the real numbers, and the complex numbers. While these examples were thoroughly investigated, a general theory encompassing all fields, a theory capable of addressing questions about their structure and relationships in a systematic way, was still developing. The tools available were often piecemeal, tailored to specific number systems, and lacking in the generality required to address broader questions. The exploration of field extensions, for instance, which involves creating larger fields from smaller ones, often relied on ad hoc methods, lacking a unified approach applicable across all field types. The algebraic structure of fields, particularly those beyond the familiar realm of the complex numbers, remained the subject of active investigation. The problem Steinitz addressed was, at its core, the problem of generalization. Classic number theory, with its focus on integers and rational numbers, possessed elegant properties and powerful results. But these results, and the techniques used to prove them, were often specific to these number systems. Steinitz sought to generalize these concepts, to extend them to a wider class of mathematical objects, to create a theory that could encompass all fields, regardless of their specific elements or their origins. He aimed to provide a rigorous framework for understanding the relationships between different fields, for classifying them, and for constructing new fields from existing ones. The importance of this undertaking cannot be overstated. A robust theory of fields would provide a foundation for understanding many other areas of mathematics, from algebraic number theory to Galois theory and beyond. It would allow mathematicians to tackle problems that were previously intractable, to unify disparate areas of study, and to discover new connections between seemingly unrelated mathematical structures. A key influence on Steinitz's thinking was the work of Richard Dedekind and Heinrich Weber on algebraic number theory. Dedekind and Weber had pioneered the use of abstract algebraic methods to study the properties of algebraic number fields, which are field extensions of the rational numbers. They had introduced concepts such as ideals and factorization in these fields, providing a powerful framework for understanding their arithmetic properties. Steinitz built upon this foundation, recognizing the potential for applying these abstract methods more broadly. He realized that the techniques used in algebraic number theory could be generalized to study fields of all types, not merely those related to the rational numbers. Dedekind and Weber's emphasis on abstract algebraic structures and their development of tools like ideals directly influenced Steinitz's approach. Their work demonstrated the power of abstract algebra for solving concrete problems, inspiring Steinitz to pursue a similar approach in his study of fields. Consider, for example, the construction of a splitting field. A splitting field, in essence, is a field that contains all the roots of a given polynomial. Before Steinitz, constructing splitting fields often involved ad hoc techniques specific to the polynomial in question. Steinitz, however, provided a general, systematic method for constructing splitting fields for any polynomial over any field. This involved defining the concept of an algebraic closure, a field that contains all the roots of all polynomials with coefficients in that field. Using this concept, he demonstrated that every field has an algebraic closure and that any two algebraic closures of a given field are isomorphic. This construction, while seemingly abstract, had profound implications. It provided a way to understand the structure of polynomials and their roots in a unified and systematic way. It allowed mathematicians to compare and contrast different fields based on their algebraic properties. It provided a foundation for the development of Galois theory, which studies the relationship between field extensions and groups of symmetries. The limitations of earlier approaches were clear. Specific techniques tailored to specific number systems, were inadequate for dealing with the complexities of field extensions and the diverse structures of fields. The existing methods lacked the generality and the rigor necessary for a comprehensive theory. Steinitz's work directly addressed these limitations. His axiomatic approach provided a common language and a set of tools for studying fields, regardless of their specific nature. His definitions of key concepts, such as field extensions, algebraic closure, and splitting fields, provided a framework for understanding the relationships between different fields. His construction of the algebraic closure, in particular, was a groundbreaking achievement, providing a universal tool for studying the roots of polynomials. The impact of Steinitz's work was immediate and far-reaching. His paper, Algebraic Theory der Körper, provided a foundation for the development of modern abstract algebra. It established the axiomatic method as a standard approach to the study of fields. It provided the tools and the language necessary for mathematicians to tackle fundamental questions about the structure and properties of fields. It influenced the development of Galois Theory, algebraic number theory, and other areas of mathematics. The paper was quickly recognized by mathematicians as a significant contribution, a work that had transformed the field of algebra. It provided clarity and rigor where previously there had been ambiguity and ad hoc methods. It offered a unifying framework for understanding a fundamental mathematical concept. The influence of Steinitz's work would resonate for decades, shaping the course of mathematical research and education. The legacy of his 1910 paper is a testament to the power of abstraction, the elegance of axiomatic thinking, and the enduring importance of seeking general solutions to fundamental problems. The axiomatic approach, a cornerstone of modern mathematics, found a potent advocate in Ernst Steinitz. His work, particularly his seminal 1910 paper, provided a rigorous foundation for the study of fields, transforming what had been a collection of disparate examples into a unified, coherent theory. This transformation, a testament to the power of abstraction, was achieved through a meticulous application of the axiomatic method, a methodology that offered clarity and precision where vagueness had previously prevailed. Steinitz's method, deeply influenced by the axiomatic approach to geometry championed by Dedekind and Hilbert, sought to build a structure from the ground up, defining a field through a set of fundamental properties. To understand Steinitz's contribution, it is essential to grasp the core of his axiomatic framework. He began by establishing a set of axioms, the fundamental rules that would govern the behavior of elements within a field. These axioms, the bedrock of his theory, define the essential characteristics of addition and multiplication, the two fundamental operations within a field. He posited the existence of identity elements for both addition and multiplication, elements that, when combined with any other element using the respective operation, left the other element unchanged. Furthermore, he stipulated the existence of inverse elements for both operations, ensuring that every element possessed an additive inverse, which, when added to the original element, yielded the additive identity, and every non-zero element possessed a multiplicative inverse, which, when multiplied by the original element, resulted in a multiplicative identity. The distributive property, linking addition and multiplication, completed the core axioms, ensuring that multiplication distributed over addition in a predictable manner. These axioms, concise yet powerful, formed the basis for Steinitz's construction of the concept of a field. From these fundamental properties, he could deduce a wealth of consequences, exploring the structure and properties of fields with unprecedented rigor. The axiomatic approach allowed him to move beyond specific examples, such as the rational numbers or the real numbers, and to consider fields in their full generality. This abstraction, a hallmark of modern algebra, facilitated a deeper understanding of the underlying principles governing these mathematical systems. Steinitz utilized these axioms to construct the concept of a field extension, a crucial notion in the study of fields. A field extension is a field that contains another field as a subfield. Steinitz meticulously defined algebraic and transcendental extensions, categorizing extensions based on the nature of the elements adjoined to the original field. An element is algebraic over a field if it is a root of a polynomial with coefficients in that field. Conversely, an element is transcendental if it is the root of no such polynomial. This distinction, fundamental to the theory of fields, played a crucial role in understanding the structure and properties of field extensions. His work provided the necessary tools for classifying and analyzing the relationship between a field and its extensions. The construction of the algebraic closure of a field in which every polynomial with coefficients in the field has a root, also stands as a testament to Steinitz's rigorous methodology. The algebraic closure, a comprehensive field containing all the roots of all polynomials, provides a complete framework for studying algebraic equations. Steinitz's approach to constructing the algebraic closure, a complex process, demonstrated the power of his axiomatic framework, allowing him to build a complete and consistent system from a set of fundamental axioms. He demonstrated how to build the largest possible field in which every polynomial has a root. To illustrate these concepts, consider the construction of finite fields. A finite field, a field with a finite number of elements, is a fundamental object in algebra and number theory. Steinitz's framework provided the tools for constructing and classifying these fields, showing that, for every prime power, there exists a unique finite field with that many elements. The construction of finite fields, a significant achievement in its own right, demonstrates the practical implications of Steinitz's axiomatic approach. The existence and uniqueness of finite fields are essential for applications in cryptography, coding theory, and other areas of computer science. As another example, consider the algebraic closure of the rational numbers. The algebraic closure of the rational numbers contains all the roots of all polynomials with rational coefficients. The elements of this field, algebraic numbers, exhibit fascinating properties, and their study is central to algebraic number theory. Steinitz's work provided the framework for understanding the structure of this field, a crucial step in the development of the subject. The influence of David Hilbert's axiomatic approach to geometry on Steinitz's methodology is readily apparent. Hilbert, in his Grundlegende Geometrie had demonstrated the power of the axiomatic method in constructing a rigorous foundation for Euclidean geometry. Hilbert's work, which provided a set of axioms from which all the theorems of Euclidean geometry could be derived, served as a model for Steinitz. Steinitz, like Hilbert, sought to build a mathematical structure from a set of fundamental axioms, emphasizing the importance of precision, clarity, and logical deduction. Hilbert's work on the foundations of geometry undoubtedly influenced Steinitz's approach to algebra, providing him with a framework for constructing a rigorous and consistent theory of fields. The emphasis on axiomatic foundations, a hallmark of Hilbert's work, was adopted and applied by Steinitz to the study of fields. The reception of Steinitz's work was overwhelmingly positive. Mathematicians recognized the significance of his contribution, appreciating the clarity, rigor, and unifying power of his axiomatic approach. His paper quickly became a standard reference, a foundational text for the study of fields. The impact of his work was immediate and profound, shaping the course of mathematical research and education. The axiomatic method, once viewed with some skepticism, became the standard approach to the study of abstract algebraic structures. The legacy of Steinitz's work is a testament to the power of abstraction, the elegance of axiomatic thinking, and the enduring importance of seeking general solutions to fundamental problems. His work provided the essential tools for understanding the structure and properties of fields, laying the groundwork for future developments in algebra and related fields. The axiomatic framework Steinitz established provided a sturdy foundation for the systematic investigation of field extensions. Building upon Kronker's work on adjunction, Steinitz crafted a comprehensive classification of these extensions, a cornerstone of modern algebra. His meticulous approach illuminated the structure and behavior of fields in a way that had been previously unattainable. Kronker, in his exploration of algebraic numbers, had introduced the concept of adjoining roots to a field. This process, where a root of a polynomial is added to an existing field to create a larger field, was fundamental to understanding the construction of field extensions. Steinitz embraced and expanded this idea, providing a complete and rigorous treatment. He categorized field extensions into two primary classes: algebraic extensions and transcendental extensions. An algebraic extension arises when one adjoins roots of polynomials with coefficients in the original field. Conversely, a transcendental extension involves the addition of elements that are independent of the algebraic structure of the original field. This distinction, seemingly simple, proved to be profoundly insightful, allowing mathematicians to dissect the intricate nature of field structures. The heart of Steinitz's classification rests on the notion of a transcendence basis. In a transcendental extension, there exist elements that are algebraically independent. These elements, which cannot be expressed as roots of polynomials with coefficients in the original field, form a transcendence basis. The number of elements in a transcendence basis, a characteristic of the extension, is known as the transcendence degree. This degree provides a measure of the size of the transcendental extension, similar to how the dimension of a vector space characterizes its size. The transcendence degree, a concept Steinitz formalized, became a crucial tool for classifying and understanding field extensions. Central to Steinitz's work is the Steinitz exchange theorem. This theorem, a cornerstone of field theory, states that any two transcendence bases of a field extension have the same cardinality. This theorem, analogous to the basis theorem in linear algebra, guarantees that the transcendence degree is well defined, meaning it does not depend on the specific choice of a transcendence basis. The theorem's significance lies in its ability to reveal the underlying structure of a field extension, offering a robust invariant that aids in its classification. The theorem itself, while elegant in its statement, is a testament to the power of abstract reasoning. Steinitz's exploration extended to the concept of splitting fields and normal extensions. The splitting field of a polynomial over a field is the smallest field containing all the roots of that polynomial. A normal extension is a field extension where every irreducible polynomial with a root in the extension splits completely within the extension. These concepts, crucial to the development of Galois theory, were meticulously examined by Steinitz. He demonstrated the existence of splitting fields for all polynomials and established the connection between normal extensions and the splitting fields of separable polynomials. Though he did work within the framework of Galois theory, his contributions provided the essential tools for understanding the structure of these extensions, paving the way for subsequent advancements in the field. The influence of Kronecker on Steinitz's work is unmistakable. Kronecker's introduction of adjunction and his emphasis on constructing algebraic extensions by adding roots of polynomials provided the initial inspiration. Steinitz built upon Kronecker's insights, generalizing and formalizing the concepts to create a comprehensive theory. Steinitz's work, in turn, provided a rigorous framework for understanding Kronecker's earlier results. Steinitz's work had a profound impact on the development of abstract algebra, particularly in the work of Emmy Noether. Noether, a brilliant mathematician, was deeply influenced by Steinitz's axiomatic approach and his systematic treatment of fields. She embraced his methods and applied them to the study of abstract algebraic structures. Noether's work on ideal theory, for instance, which explores the properties of ideals in rings, was directly influenced by Steinitz's emphasis on axiomatic rigor and his classification of field extensions. The abstract methods and structural insights pioneered by Steinitz were adopted and expanded upon by Noether, transforming the landscape of algebra. The influence was not merely about adopting techniques, it was about embracing a new way of thinking about mathematical structures. Steinitz's work provided a model for the axiomatic approach, which would become a central tenet of Noether's work, solidifying her status as a foundational figure in modern algebra. The reception of Steinitz's work on field extensions was overwhelmingly positive. Mathematicians recognized the clarity, rigor, and unifying power of his axiomatic approach. This paper quickly became a standard reference, a foundational text for the study of fields. The impact of his work was immediate and profound, shaping the course of mathematical research and education. The axiomatic method, once viewed with some skepticism, became the standard approach to the study of abstract algebraic structures. The legacy of Steinitz's work is a testament to the power of abstraction, the elegance of axiomatic thinking, and the enduring importance of seeking general solutions to fundamental problems. His work provided the essential tools for understanding the structure and properties of fields, laying the groundwork for future developments in algebra and related fields. The ramifications of Steinitz's contributions resonated far beyond the immediate landscape of field theory. His work provided essential tools for comprehending Galois theory, a cornerstone of 19th century algebra, even without a direct engagement with the theory's complexities. Galois theory, developed by Évariste Galois, explores the relationship between polynomial equations and their solutions, utilizing the concept of groups to determine the solvability of equations by radicals. Steinitz's framework offered a more general and structured approach to understanding the fields that are involved in Galois theory, which facilitated the advancement of the field. His rigorous treatment of field extensions and their properties provided the necessary language and conceptual framework for mathematicians to analyze and manipulate these structures with greater precision. This indirect influence, though subtle, was crucial. The axiomatic approach, a hallmark of Steinitz's work, became a guiding principle for subsequent generations of mathematicians. This method, which prioritizes the derivation of theorems from a set of fundamental axioms, provided a level of clarity and rigor that was previously absent. It encouraged a shift away from ad hoc methods and towards a more systematic and unified understanding of algebraic structures. This shift was particularly evident in the development of abstract algebra, a field that Steinitz's work helped to define. The study of groups, rings, and fields, divorced from specific examples, became a central focus. This move allowed mathematicians to explore the underlying structures and properties of algebraic objects in a more general and powerful way. The influence of Steinitz's work is palpable in the work of Emmy Noether. Noether, a brilliant mathematician, built upon Steinitz's foundations, expanding the scope of abstract algebra and creating new mathematical areas. Her work on rings, ideals, and modules, which are fundamental algebraic structures, was profoundly influenced by Steinitz's axiomatic approach and his focus on the properties of fields. Noether's contributions, which include the development of the theory of ideals and commutative rings, built directly on Steinitz's work. She recognized the power of his approach and applied it to a broader range of algebraic structures, thereby solidifying the axiomatic method as a central tenet of modern algebra. Her theorems, such as the famous Noether normalization lemma, have had a lasting impact on algebraic geometry and commutative algebra. Emil Artin, another prominent figure in the development of abstract algebra, also recognized the significance of Steinitz's work. Artin, known for his contributions to class field theory and the theory of braids, was influenced by Steinitz's emphasis on the importance of field extensions and their properties. Artin's work on algebraic number theory, which studies the properties of algebraic integers, heavily relies on the concepts and tools that Steinitz developed. His work on the Artin-reciprocity law, a cornerstone of class field theory, demonstrates the profound impact of Steinitz's ideas. Artin's use of field extensions to understand the structure of number fields and his development of the theory of valuations are a direct consequence of Steinitz's contributions. The principles established by Steinitz continue to find relevance in modern mathematics, including areas that would have seemed distant from his original focus. His work on field extensions has found applications in coding theory, a field that deals with the design and analysis of error-correcting codes. These codes are used to detect and correct errors in data transmission and storage. The construction of finite fields, which Steinitz pioneered, is fundamental to the design of many coding schemes, such as Reed-Solomon codes. These codes are widely used in digital storage, data transmission, and other applications. The properties of finite fields, first explored by Steinitz, allow for the creation of efficient and robust coding systems. Furthermore, Steinitz's insights have found applications in cryptography, a field that is crucial for securing digital communications. The construction and properties of finite fields are essential for the design of many cryptographic algorithms, including the Advanced Encryption Standard, or AES. AES, a widely used symmetric key encryption algorithm, relies on operations within finite fields to provide strong security. The ability to create large, complex finite fields, which Steinitz's work made possible, is essential for the development of secure cryptographic systems. The enduring importance of Steinitz's work in cryptography is a testament to the deep connection between abstract mathematical concepts and practical applications. The axiomatic approach that Steinitz championed has also proven to be invaluable in computer science. The formalization of mathematical concepts using axioms and logical rules is fundamental to the design of programming languages, the development of formal verification techniques, and the study of computational complexity. The clarity and rigor that Steinitz brought to the study of fields have inspired similar approaches in computer science, where the need for precise definitions and logical reasoning is paramount. The legacy of Steinitz's work extends into the realm of computation, influencing how we understand and interact with information. The impact of Steinitz's work extends beyond the realm of pure mathematics. His approach to field theory has influenced research in physics, particularly in areas like quantum field theory. The concepts of fields and field extensions are used to describe the behavior of elementary particles and their interactions. The techniques developed by Steinitz have provided a framework for understanding the mathematical structures that underlie physical phenomena. The profound implications of his work are still being explored. Steinitz's work spurred the development of algebraic geometry, a field that studies geometric objects using algebraic methods. The properties of fields and their extensions are essential for understanding the structure of algebraic varieties, which are sets of points defined by polynomial equations. The concepts introduced by Steinitz, such as the notion of a field's characteristic and the concept of algebraic closure, are fundamental to the study of these varieties. His work provided the necessary tools for the development of this field. The reception of Steinitz's work was strong. His contributions were recognized for their rigor, clarity, and unifying power. His paper on field extensions became a standard reference, a foundational text for the study of fields. The axiomatic method, once viewed with skepticism, became the standard approach to the study of abstract algebraic structures. This transformation, in large part, is due to Steinitz's work. The enduring significance of Steinitz's contributions stems from his ability to provide a general and rigorous framework for understanding fundamental mathematical structures. His axiomatic approach, his meticulous attention to detail, and his focus on the properties of fields had a lasting impact on the development of mathematics. His work provided the essential tools for understanding the structure and properties of fields, laying the groundwork for future developments in algebra and related fields. The legacy of Steinitz's work is a testament to the power of abstraction, the elegance of axiomatic thinking, and the enduring importance of seeking general solutions to fundamental problems. The profound impact of Ernst Steinitz on mathematics transcends mere compilation of results. It resides in his profound restructuring of the very landscape of algebraic thought. His work on field theory, particularly the seminal treatise, served a pivotal role in the transformation of abstract algebra, establishing it as a rigorous, axiomatic discipline. Prior to Steinitz, field theory, while possessing a rich history of specific results, lacked a unified, comprehensive framework. The study of fields was often piecemeal, focused on specific examples, and lacked the generality that would allow for deep exploration of their essential properties. Steinitz, by embracing the axiomatic method, provided the essential architecture for a systematic and coherent study of fields. The genesis of this approach can be traced to the burgeoning interest in abstract algebra during the late 19th century. Mathematicians, grappling with the inherent complexities of number theory and the emerging concepts of group theory, recognized the need for a more general and abstract approach. Dedekind's work on ideals in number fields, for example, demonstrated the power of abstract algebraic structures. However, these early explorations frequently lack the unifying power of a comprehensive axiomatic foundation. Steinitz recognized the need for such a foundation, and his work provided it. Steinitz's contributions went beyond mere systematization. They produced fundamental new insights. His classification of fields, his development of the concept of algebraic closure, and his exploration of the properties of field extensions were groundbreaking. His work on the existence and uniqueness of algebraic closures is particularly noteworthy. The notion of an algebraic closure, a field containing all the roots of a polynomial, is now a fundamental concept in algebra. Steinitz demonstrated that every field possesses an algebraic closure, and that this closure is unique up to isomorphism. This result, initially a technical advance, became a cornerstone of field theory. The immediate impact of Steinitz's work was evident in the rapid development of abstract algebra. His treatise became the standard reference for mathematicians working in the field. It provided them with a clear and rigorous framework for understanding fields, and it stimulated further research. For instance, Emmy Noether, a student of Paul Gordon and a key figure in the development of modern algebra, was profoundly influenced by Steinitz's work. Noether's work on ideal theory and her development of the concept of a module, which generalized the concept of a vector space, were directly influenced by Steinitz's axiomatic approach. The abstract nature of her work, the emphasis on structure, and the use of axiomatic methods can be traced back to Steinitz's influence. Furthermore, Steinitz's work had a significant impact on the development of Galois theory. Galois theory, which links the solvability of polynomial equations to the structure of their Galois groups, relies heavily on the properties of field extensions. Steinitz's work provided the essential tools for understanding these extensions, and it helped to clarify the relationship between the roots of a polynomial and the structure of the field in which they lie. His work offered a more profound understanding of the theory. The reception of Steinitz's work, while initially met with some resistance to the abstract nature of his approach, was largely positive. Some mathematicians, accustomed to the more concrete methods of the past, were initially skeptical of the axiomatic method. However, the power and generality of Steinitz's results soon won them over. The clarity and rigor of his presentation, combined with the depth and originality of his insights, quickly established his treatise as a foundational text. It was quickly recognized as a major contribution to the field. Subsequent generations of mathematicians built upon Steinitz's work, extending and generalizing his results. For example, the theory of valuation rings, which plays a crucial role in the study of algebraic number theory and algebraic geometry, relies heavily on the concepts developed by Steinitz. The work of Wolfenkrall, a student of Isaicher, on the theory of valuations, for example, was directly influenced by Steinitz's work on field extensions and algebraic closures. Krall developed a general theory of valuations, which provided a powerful tool for studying the arithmetic properties of fields. This work, in turn, influenced the development of modern algebraic number theory and algebraic geometry. The enduring legacy of Steinitz lies not only in his specific results, but also in his profound influence on mathematical methodology. His emphasis on rigor, his commitment to axiomatic thinking, and his focus on general solutions to fundamental problems have had a lasting impact on the way mathematicians approach their work. Steinitz taught mathematicians to think abstractly, to seek general principles, and to appreciate the beauty of mathematical structure. This legacy extends far beyond field theory, influencing the development of other areas of mathematics, including topology, functional analysis, and computer science. The axiomatic method, so central to Steinitz's approach, has become a cornerstone of modern mathematics. It provides a powerful tool for organizing and understanding mathematical concepts, and it allows mathematicians to explore the underlying structures of mathematical objects. The axiomatic method allows for the construction of rigorous proofs and the development of general theorems. The method has been adopted across the spectrum of mathematical disciplines. Steinitz's contributions offer an enduring lesson about the power of abstraction. By focusing on the essential properties of fields, rather than their specific examples, Steinitz was able to unlock a deeper understanding of their structure and behavior. His work demonstrated that abstract mathematical structures can be incredibly powerful tools for solving concrete problems and for understanding the world around us. His work also showcased the importance of rigorous thinking, attention to detail, and the pursuit of general solutions. In conclusion, Ernst Steinitz's work represents a pivotal moment in the history of mathematics. His contributions to field theory, his embrace of the axiomatic method, and his profound influence on subsequent generations of mathematicians have secured his place as one of the most important figures in the development of modern algebra. His legacy continues to resonate in contemporary mathematical research, and his work provides a compelling example of the power of abstraction, rigor, and the enduring pursuit of mathematical understanding. The enduring relevance of Steinitz's work is a testament to his intellectual vision and his lasting impact on the world of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.